No,
equation.
no, I don't care what is physical. No, I clearly solves the problem. Literally, this is like the hardest thing they think it is, but this is easier thing for me. So, this is for Maslow's last theorem. So, I really start my broadcasting, but I'm really recording here. But I got my pen and paper literally. But this is the last theorem. This is what I'm saying.
So relativistic speeds. We're
So this is
used
the
to
last.
seeing
This is like how I
equations
watch the
like
television. I got my notes.
E equals mc squared or momentum equals mass times velocity. Even if you've never taken a physics class, you've probably run into E equals mc squared. But this isn't actually the whole story here. It's actually E equals gamma mc squared. And we've got momentum equals gamma mass times velocity. So gamma here is the Lorentz factor, which is 1 over the square root of 1 minus the velocity squared over the speed of light squared. So at really low speeds, this is irrelevant, and we change our equations to E equals mc squared, or momentum equals mass times velocity. The Lorentz factor is also incredibly important when you want to figure out how much the length of something changes or how time dilation works. So the length to an observer is equal to the length of the object divided by the Lorentz factor. And the time for the observer that's stationary is equal to the Lorentz factor times the time that the object is experiencing. So let's take a look at what happens at normal everyday speeds. So when our velocity is much, much less than the speed of light, this term that the velocity over the speed of light is almost zero. So when you're dividing a small number by something on the order of 10 to the 8 meters per second, it becomes almost so close to zero that we just call it zero. And then what you're left with is 1 over the square root of 1 minus 0. So that's just going to be 1 over the square root of 1, or 1 over 1, or 1. And when you multiply anything by 1, it's just going to be itself. So that's how we end up with E equals mc squared, or momentum equals mass times velocity, or length equals length. So let's do an example where we have a velocity of half the speed of light.
It's two observers watching a state of relativity. Two red waves, you get two sides. People that relativity. If you put someone on the moon and someone on the moon goes, it's just like the kind of time dilation. That's what the relative reality is. A reflection of light, but they don't really via medium, and that's what all it is. But this is just like straight driving.
So that's 0.5 times c. So how much would this change our equations? So the Lorentz factor is going to end up being 1 over the square root of 1 minus 0.5 times c over c. This whole thing is squared. So our c's are just going to cancel out, and we're just squaring 0.5. Of course, you can put in the actual speed and the actual speed of light, but when you have some percentage or some fraction of c, you can just use that, and the c's cancel out, and it becomes a little bit easier. So this is going to leave us with 1 over the square root of 1 minus 0.5 squared, which essentially is going to give us 1 over 0.75, take the square root, and that's 1.15. So even at half the speed of light, we're only changing by a factor of 1.15. So that means our energy is going to be 1.15 times what it normally would be at lower speeds. And same thing with momentum, 1.15 times classical
But this is
momentum,
E. This is not why.
and
Oh,
our
this
time
is
is only
E.
going to
Of course,
dilate
the
by
11. This is a
1.15.
Hamiltonian, but it's flipped. This is not E.
However,
This is
length
not
works a little differently.
It's not
It's divided by this factor. So our length is going to be 1 divided by 1.15 times the length of the moving frame. So 1 divided by 1.15 is just 0.87 times the normal length. So obviously this is going to change by a much bigger factor if you're much closer to the speed of light, like 0.9, 0.95, and so on. It'll change much less if you're at 0.1 times the speed of light. So this video was basically just to review how the Lorentz factor works and how it changes things.
Basically, people get it wrong.
Get ready, builders. Snowflake build is taking...
So in the last video, that x equals to ct prime.
People are getting wrong. A lot of things.
Now let's just assume, and we're sitting in the K system.
So x prime
So what this
equals a of x minus b minus c. This is like the roots, but the roots are what separated from the quotient for the problem which you get. Ct was the light and the time of the derivative. This x to prime equals ax minus bct, but it's just the quadratic equation via the determination of a prime number. So basically, this x prime equals ax. This is ax is like the variables in a squared plus b x. Basically, this quadratic equation is just quadratic equation, but it's just a programmer formula because negative boy x basically only got so x negative boy couldn't side basically x equals y when the y equals to y. X prime is y equals negative boy plus or minus square root good inside let's go radical part, and that is good inside that's 2 AC wait 4 let me write it down because I got it wrong. So this I'm modeling right now. I know I'm modeling, but basically people are getting it wrong. I know how to solve this problem, but I don't want to do it mathematically because I'm cooking, but I didn't plan to do it. A negative boy equals a negative boy couldn't decide where to go round to a negative boy. I'm fucking up my equations literally because I'm rushing because I didn't plan to do it like this kind of thing, but I'm gonna do it anyway. But because I'm doing it improperly, it's like a negative boy and b couldn't decide to go wrong from a b square. He's either not to go Mr. 4 or something. What's wrong with 2n? So basically, this is quite a problem. This is what determines the symmetric equation. What is a parabola? A parabola. Like let's just when you have two terms, x squared plus y squared equals r squared. If the radius is squared, you double the radius, you get a diameter. Diameter just defines the parabola in the pi parabola. So just get the pi. You get radius times 2 is the diameter, and that's just between 1 and 0, 1 and 1. So the radius is very important to get because I have the sign notation for it, and that's basically the vector model of it. So if you remember the conjugate pair rule, what I call you get x squared minus y squared equals minus r squared, and this will be two sets of equations that you get. So basically you get if you understand, like literally it's what it is, but I'm making it clearer now because it's meant to be there. So you get r squared, which would be 0.5 squared, which would be 1, but this is minus 5. 0.5, this would be minus 1. Because when you square it, you are 1. You're duplicate. So this is how you derive it. But you can have a kind of cool set of it. But you can get something that's in that state. This will eigenvalues. Next to nothing. But I'm gonna give you my take on this. I don't want to watch this video and waste your time. So I'm going to give you my take on it. So this way you get it. Because I got the screen positive way. So here's where you get it. But this way you get it in time. So I'm going to come place right down with it. So what this means is you get the number 1 to minus 1. Literally, that's what you get. This is matrix 1 to 1 minus 1. But as the final number, it's r squared, which is double. R squared is what? A radius. Squared is 0.5 times 2. 0.5 or times 2 or 0.5. But you get double, and that's the ratio of 1 minus 1 minus 1 based on the axis you're on. Note on east south, east and east and west. And basically this is how it works in the kind of polar system. This is why I love polar coordinates because they do with spin. I never ever use Cartesian coordinates because it's just anti-practice. It's a bad because you're working with spin. Since we go that rotates on an axis. and that's why I don't want never use calculus constant because if you didn't come unless I want some calculus state of a calculus system, I can use it. But basically, if I'm storing something statically and it's static still state, like it's active, but it just updates when it needs to. Which is still so it just come for computation that needs to be stored, like the pi number pi. So I don't have to recompute the whole thing and the state I'm already in. So the quantum field span, my system updates without what is the quantum noise or fluctuation in the system. I love fluctuation, but wave propagates in oscillation. So this is like kind of not stupid to me. So this one is talking about x prime a squared minus b ct. This is just the kind of square root of the system, but it is the derivative of time. So the time is ct, which is constant time of speed. But this is the same thing as what the Rayleigh factor. So he's taking the derivative of all the variables. I just know that intuitively because Rayleigh factor is just the if t equals 0, x prime equals a of t. This square root. Am I wrong? Let me just see. Basically, I didn't see him derive it, but I want to see what it.
Stop using ChatGPT and Canva like children's toys. Here's how to use them right.
Stop.
So,
but it's like a
Squared.
So it's like
The left-hand side is equal.
He's got some of this thing here, but this is s squared equals to s squared cubed. But this is like I don't even know what problem. This is the Rayleigh transformation. So what is he trying to derive? A Rayleigh transformation. This is not really the thing he's trying to do. He's going to do it, but doing poorly. So I'm gonna try to do the same thing, but better. So I don't want to look at this method because it's really difficult to make my mind because he just has a lot of mistakes I see here, and if I keep watching the video, I can make the same mistakes. So I'm gonna leave that. I love the diagrams. The diagrams are very good because he did them himself. But I'm not gonna just follow. I'm gonna use the same analogy because I love teaching people too. But I'm trying to divide the Rayleigh structure as a transformation into this way. Because what's my drink? What's my joke? I am relentless. I mean, this is what education could be. It's not more in gaming. This is what education could be. Honestly, this is what education could be relentless. So let me try to do it now. Because I've got some music to play. So you go to e to the power of I squared equals 0. Equals plus 1 equals 0. Plus 1 equals 0. But you don't need the plus 1. You never need plus 1. Because e to the power of I, e to Euler's identity, Euler's number to the power of I pi is equal to minus 1, which is equal to I. So that's what you're gonna need minus 1. So you don't need plus 1, you need minus 1. But they all share a negative state, something of this term. Because it's negative, we share I'll get to what I'm saying, but this is what I'm trying to do. So we share a negative 1 state, which is negative 1, but literally they share that because it's literally just negative 1. This one just because it's like Euler's identity, so they have a negative 1 can do. So if you transform this on an axis, you get a negative growth. Think of things going oppositely on a system. I'm going to try to give you calculator. Give me a calculator out. So my calculator is this. So if I type in Euler's number is minus 2.71828188284. But this is how many 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9 numbers. Minus 2.718287 wait. It's 2.7182881. Oh, 281, not 282. So I'm saying because 81, 82. 82. This kind of thing now. 82. 82. No, sorry. So you get the decimal. This is the minus 2 is this growth negative direction. That's what I'm saying because it's negative. So you have some actually e pi I. So this is a growth or negative growth in other directions. This is why it matters. It just shows it works. How math works. So you can just get a negative equivalent of it. Pi, number pi. You get pi. Pi is a negative 3.141. I love pi, but to decimal precision. So 6153589. This is pi. I love pi. This is Euler's number, which is the standard growth. So we have Euler's. How you compute Euler's number? It's just you have something in the interval time. Let me compute. I don't give you example. Something happens twice. For example, let's get 100% of something. 100% interest per. 10% interest. It's a growth function. So if a bank gives you what 50, I don't like that one actually, because that one's too easy to use, but it's just the foundation of everything, so it's easier. So we get a bank for 1 early identity, so get 100% of something. So interest is 10% a month, half every half month. So what? You double interest every 4 weeks. Every 4 weeks, that'll be 100%. No, 10%. No, you get 50% a month. 50%, and if you get half of half every month. So every month. So in 4 months is 32. 7 times 4. That's 28 days. 28 days. So half of that is 12. So look at this is just how you grow. How you grow. So we become 50%. So if you have what £5, £5, it becomes in 2 weeks. In 1 week, it becomes you have put £5 in a bank. In 1 week, it will become what? £5 in 1 week. £5 basically accounts this. £5 is like I'm very bad of me. I'm not even holding it properly for myself. Actually, I hate kind of this. So it's like I'm a bad hand to try to solve the problem. But that's what I'm saying. You get £5 per £5 1 week. £5 1 week is what? 5 times 1. So that'll be a quarter of the system. 5 times 1 quarter. That'll be 5 times 4, 20. 20. We have to add this 20. 5 times 4 is 20. I'm right. £20. £20. So you get £20 in 1 week, but you get 4 weeks of it. So 5 times 20 is £5 plus 20 is what 25. So you see now 25 and 25%. So this is how all this number is. So this 20 is just the Euler's identity, but they get dash times 4. So every 4 weeks they now get a second week. Now the second week this doubles. It doesn't quadruple. It just doubles. So you now get 20, 25. Now 25 is just a state the money you have now in your back. 25 times 5. Because the seed is still, so with the 5 is preserved. Because you got a new state of 25. That's a double. 25 times 2 over 4. Over 4 is 20. It's 100. 100 times 2 is 200. So you now get 200. Wait, am I right? No. 25 times 4 is 25. No, I'm not calculating. I love my 25 times 4 is what? 25 times 4 is 100. 100 divided by 2. 100 divided by 2. 100 25 times 4. 25 times 4 is 100. Oh, basically, 25 times 4 is 100. So 100 divided by 2 is 50. So you now get 50. So you get basically this 2 and 50, you just add them up and it'll be 100. So you get 100%. But this 100 is growth, full growth of the system of house. But yeah, it shows it works. So back to the example. So I would say this example is not wrong. It just needs more fine tuning. So this is trying to develop a low transformation. This low transformation is very ambiguous. It doesn't really align with the principle I'm really going with. But there's some kind of misalignment with the actual choice. But he doesn't know what it is at this time. But he's doing special relativity. So this is Dean Bean. What time? Dean Bean. So this is what I'm saying. So this is like my first work family. So what am I trying to do? So basically, why this problem matters to me, first of all, is I don't talk about the problem here, what matters to me, but I'm going to write down. So this is a Rolls transformation. So I'm going to say why I need them, because I can't forget. If I read it right, I forget them. So you get 4 axes of 4 axes. So you get 4 polar coordinate systems. That's like 4 quadrants. So you have 4 quadrants. You get the left quadrant, which is what? The left one, which is 1 minus 80, 1 plus 80, you get 4 quadrants. This is like the 4 axis, 90 degrees, minus 90 degrees. You get 1, 2, 3, 4, and you go anti-clockwise. Those go anti-clockwise. They are IV, which is 4. So this is the top left quadrant is 0 to 90, up and down, and that will be basically secant and the dual system of our system. So that's what I'm saying. But the problem with the Rolls factor is like I don't remember the Rolls equation. Basically, the Rolls factor is a crucial component in theory relativity defined by gamma. Gamma function units. So I'm saying. But it's like, look, I love this video. I'm gonna subscribe. I'm gonna sign in. I'm gonna sign in. So Rolls factor is the prevailing implication of energy conservation. Wow, we do the as objects approach light speed. What's the cause for include value? Oh, this is about energy. That's what it matters. I do have my energy framework in mind, which is electrolysis in mind. But gamma, as energy, basically, this is what I'm saying. It's basically transformation. This is like a solvable problem. And theory of relativity. Why would you guys just say so? But this is for Fermat's last theorem. This Lorentz factor. I'm working the wrong framework. I'm looking with the wrong thing. But this is a Lorentz transformation. This one I wanted to work on. But I don't want to talk about formula routers, so get this one done because I want to do this for a long time. So the Lorentz factor is just this equation. This question is not scary. It's just like like I don't remember, but just she's gonna see, but I don't really want to remember it. I haven't done it in a long time, so I just like I just take it as a symbol and a glyph. I don't even want to look at it, but it's so important when you want to write it down, and that's the problem I have sometimes. So the derivative is divided by V is the derivative and the C is going to vacuum. B is the distribution ratio, and T is going proper time. From okay, basically this is all wrong. This is all like not wrong. It's I won't say it's wrong. I won't say it's wrong. I love it, but it's too linear. It's too linear. I just what I don't like about it. It's not it doesn't respect anything. That this is a problem. This is gamma factor. The gamma factor is the lowest term with the gamma factor. It reminds me. It's like when you say gamma, I'm thinking of gamma as in the gamma waves it propagates. Is that why they call it gamma factor? But I love it because it just gives me more clarity because I don't think about the problem in another way. That's why I love it. Gamma term, gamma factor, Lorentz term. A dimensionless quantity, expression of how much measurement dimensionless. That means it has no volume. No, it has the volume, and that volume is noisy. That's all it is. Basically, if you say dimensionless, it has the volume. But that volume is noisy. You can't really pull information out with the tools you're using. So basically, I got it right. I know I'm doing. So let me try to define it properly. How many times have I got? So this this is computation. So what is what's it called? 1, 2, 3, 4. Momentum. Something moving at a distance. This is the momentum of the large function. Derived by stop it. For my last story. No, this is the wrong one. Applying the rapidity to hyperbolic angles time. But this is the alternative representation of the momentum rapidity. The rapidity function of the momentum is the change of the curve at the time point in time. But this is not fully formed. It's like kind of disjoint. This is graphical progression. So it's kind of linear. It doesn't make any sense why you're doing it like this, guys. Let me just tell you how I do it. Y left and this is why I do sigma form. But the B bottom is beta. Beta waves, like beta waves, no. Basically, this is beta waves. This is the version of 9s. Basically, I'm using my relay system together. I don't want to fuck this up. Let me get a little more fun. So I know a problem here. Namdi, this is an easy problem for you. I know it's not stupid. It's not stupid, but I can solve it right now. I need to do it. Let me get some dinner. But this is my food here. This is something. Give me 1 second, guys. I'm trying to do it because I've got food here to eat. So I got food right here. It's not that hard to get it. I just have to like relax it. This is what I have to do. Basically, I got my guys. This is take a bite. If I can't eat it, if I don't eat, I will not solve the problem. I will not solve it my way. I will not be actually solving the problem. And I don't want to make mistakes, and I don't want to make mistakes. And I want to make it all right. Yeah, all right. So I'll eat because I'm being silly. This I wouldn't even my own ass. So literally, it's because I love my life. I mean, I love it because it's good enough for me. It's not good enough. I don't want a simple life. I want a great life. I want the best life of my life. No, nothing. So this should be recorded. This I'm cooking, guys. Like literally, I still don't fucking care. I should be checking this on YouTube too. So I should be doing that. This is not the way we're checking this. What I'm saying. So this one is solvable for me. I just know it's something. This is why I just cooked. Just like, well, I can't find it there. Basically, I can't find it there now. I'm on the cool. It's all cooled down already, but it's live. Right. But look at this one. I'm gonna eat. It's got like a lot of juice on it, but it's not really I don't think it's good for me. Wow. Guys, this is like rice, but it's rice that I just cooked up. Like look at this. This is just no. Oh wow, man.
Oh, it's so sweet. Ah, sweet potato. Of course it's sweet. Look, it's good. It's good I made it. Because, you know, if I didn't make it, I would have been suffering. Let's go with the problem. I got a few problems to tackle, but I'm gonna put that problem on the side. But the first problem I have, but I will bring it down. So I got it written down, and I got it written down. Just brought myself some dinner. It should be fine, guys. It should be too bad because there's nothing bad happening tonight in this kind of camp. Sorry. I go up later. Okay, I just eat that. I'll go. Okay, but I make videos. So what time you want me to go?
Half an hour more.
Half an hour? Okay, fair long.
Yeah, you can stay half an hour more.
Thank you. Because look, it costs me so. Thank you. It means so much to me. You know, no, but it means so much to me because you know, my family know here, my head spin. You don't know what it means to me because you know, if in my house, I'll be down here everything. You know, but you mean you want to do. That's what it means to me. You know me you care. I mean you want to do. You know, that's what I mean. You know what I'm saying? No one told me they care. They don't tell me they care. They tell me they care. You know what I'm saying? So me, I know everything because I know how I process information. If I don't know how to do something, why come here? You know, it's smart.
I know you are so smart.
Look. I'm smart because I know what I do, how I do. I plan everything. You know, that's what. Sorry, that's what we're meant to do. You know, no matter if you grow up, look, we're a team. You get the family support. You get no. You know, no matter if you're bad enough, but don't teach you that. You know, you don't get it because you need it. Then you know, don't forget how to look. Boy, I'm tired of here. I try everyone, but why I'm really angry is they don't respect me. You know, if they respect me and know I'm smart, why be here? You know, they say, well, you know your job. You know, I know it'll be a long time with you, but 6 months is too much for me. I'm tired of it. You know, I just know how I do. You know, if I don't get a plan, I tell my plan, what's your plan? Yeah. If I don't get a plan, why tell it? No, I don't just tell you my plan because my plan get house. You know, if I don't get house service, why tell you my plan to get house service? You know, if I make my house and these people are rubbish, I don't just tell them how they do the service. It's not the same. No matter if they do or not, that's how we work in Nigeria. Look, you know, in Nigeria, my dad don't teach me. My dad teach me what? How I know my dad? I try to go. My dad has a fire shop, promotion shop. Yes, he gave me fire, sell fire. So you see me 1 week, 2 weeks, 1 week I learn. 2 weeks I run shop. You know, you don't believe me, but I know how to sell this fire shop. You know, because I know how to sell it. You know, I know how to sell it because I know how I do in Nigeria. Because my father took me when I was 5 years old, 4 years old, 6 years old, and I was selling this kind of thing. That's how I know how to do. That's what you meant to do that for your child, everything. But you didn't child know how to do in the shop. That's what we do in our country. Because that's what you see this man here, this Arabic man in his country, his son, teach him. He teaches his son. But he's come out to run shop, he calls all his son. You don't need to be that old to run the shop, you know what I'm saying? That's what law is stupid in the UK. You know, because I run shop for my dad, I sell fire fish, I do everything my dad, and I still get money, you know, I still grow myself. Look, this country rubbish.
You need the light.
Yes, I'm done. I really want
the light, please.
Yes. Okay?
If you don't mind.
Okay, fine, okay?
Yeah.
Okay, this is fun. But you know, you really tell me so just to but you know, don't need it now. You know, it's hard because you don't need support. You know, when you get support at wrong age, that's what I said. You know, if you give us support, if your son runs your business, you won't do business, you won't be doing too much work. No. And that's what my dad did when he was young. Now you know do get yourself fine. Just shop like this. His dad do this business. This is my dad. How you do now? You know, you wait for me that place and wait for that place. That's where I go. That's where I go. That's where I go back. My dad has saying he do like that. He has to shop. And that shop's still there. But that's the shop in that place. You know, that's the dad's place. And I have it now. That's what I'm saying. I have things I want to do in my country. But if I look, I'll just give you an example. That's what I tell you. You know, if I don't give you example, it doesn't make sense. And I do like that, I do not be here. That's only know how I do, you know, how I get, you know, and that's why I say that it's problematic. So, what was I? So, literally, I've been eating, yes, I've been eating. This is like, basically I've got this on my lap here. And my salt is there. It's not really salty anymore. But I'm going to do chicken here. This is so. This is all done. He's so, he needs it. He needs it. This sauce is not really cooked. Okay. This is so good, huh? No. This is where it came from. Look at this. There's no chicken here. It's not needed. I mean, I'm gonna try it. I'm gonna get some to steak, but every put it off. No, at least just put too much in it. But I'm gonna spend 30 minutes down here. You know, I have a chance to do so. I'm gonna fuck it up. The fork is fine. So we'll do that. Because I'm going to keep a steady halfway, like with the sun, control my temperature. So I can solve a problem. A math problem, a physics problem. Because sorry, I did apply physics. I did apply physics. I did apply physics. So I should be able to solve it properly with my framework already invented. So it's meant to done properly. It's like I'm like autistic style description. I'm with EDC. It doesn't taste salty. Interesting. Okay. It doesn't taste salty at all, is that? I mean, when I put salt in, it tastes salty. I think I did it perfectly this time. I don't know. Yeah. Okay, it's tasted there. It's so salty. Okay. Now let me mix it properly because I know I'm tasting salt. I know I'm tasting the salt. I know. You know, I always take the salt first. That's how I normally do it. You know, because I like a salt. It's kind of like a, you know, it's not being cooked, so I have to mix them. The salt usually, I don't put salt normally properly because it needs to be done properly. So the salt is not properly done. So when I put salt, when I put a little salt, I have to mix it, but I don't mix it initially. I just have to get it sweet. So because of sweet tooth, and that's what I'm saying. The problem is I have too much of sweet tooth, but it's not sweet because I like sweet things. That's what means like sweet things. But this is just rice and pasta, a little bit. I'm going to Japan. Like, just Japan. But you know, I'm gonna go there properly. So, this washing machine is under here. I mean, it's supposed to be like this. Honestly, I swear to God. Okay, let me just oh, this is Eunice. But this is not the frame from the hand of man. This is not even stopping. Okay, let me just try to. I just stopped. This is over 1 hour. I don't know. No, it's gonna be 45 minutes. 45 minutes will be 8 minutes left. So let me continue. So basically, this was where I was. No. So basically, this problem was basically this is the measure of gamma factor. I don't know what the gamma factor is. It's the measureless quantity. One dimension, quantities of one or dimension one. Quantities the quantity person defined in a manner it prevents the ambition of the use of measurement. Typically expressed as ratio that aligns with our system. Continue to define the units. For instance, alcohol by volume. Volume is a volume problem. This one basically I'm gonna try to radian serves the angular measurement. Yes, 2 pi, yes, 2 pi, starting 1, 2 pi, equals to 6. Basically, this one is saying, okay, so let me have a go of this. So basically, history, dimensional is this. Quantities have dimensions, yes. Dimension quantities is a regular size. Oh my goodness. But what's the dimensionless quantity? Buckham's notation, pi theorem. The Buckham's theorem doesn't depend on the space unit, but estimates of theories ratio, Boyle's law. But this is very buoyancy. Boyle's law is the Boyle's it's like a gas law. So this like press temp. Oh, this same thing.
Press it. Oh, basically, yes, the same problem here. This is the main problem I'm trying to address. So this same thing. This is where it all starts for me. Let's say Boyle's law demonstration. Let's see what this is. This is Boyle's law demonstration.
In a demonstration of Boyle's law, we'll place a balloon in a vacuum bell jar. We'll apply a vacuum which basically pumps out the air in the bell jar. The pressure outside the balloon will be greater than the pressure inside. The balloon expands to try and equalize the pressure. Volume and pressure are inversely related to each other. When we release the vacuum, the pressure increases and the volume decreases. As another demonstration of Boyle's law, we will put a marshmallow peep into our vacuum jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the peep will expand to try and equalize the pressure. When we release the vacuum, the pressure increases and the volume decreases. As another illustration of Boyle's law, we will put some shaving cream into our vacuum jar. The shaving cream contains...
Oh no, shaving cream. So pressure.
Illustration of Boyle's law. We will put some shaving cream.
Shaving cream. Oh, shaving cream, just like a descriptor.
Air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
Okay. Okay. I don't hate this, guys. I just think it's different, like autistic instruction. That's what it is. Power over velocity is a time. This is power over time. This is just like, this makes all the sense, man. I'm just making a lot of sense now. Namdi, this is making too much sense. Okay, let's do it properly. Let's do it this way. So, to mention, let's do some definitions. So we go for using pi frameworks. Okay, using pi to model this. So, before I start doing this, I have to state some things. So we got which I'm trying to model this as three things. We got some 3 dimensions of axis. I'm gonna use my model to do it. I'm gonna put my model. So I'm gonna put my diagram. But I'm gonna put it in my pocket for now. But it's the same thing I got right now in my head already. It's already good in my head. It's already done in my head. So I'm gonna put it in my pocket. Sorry, I don't want to lose it. Because I'm putting it in my pocket. So here I've got what I call a dimension of space and time, and that is a lepton. 0.5 positive. 0.5 is the lepton, and we get half 0.5 as well. 0.25, and that's a mu1. And the 0. Opposite end of it is 0. Measure of matter is what? A 2r. This I'm saying. This is the same thing as the axis. We get as an axis. Because you are using this kind of model number. So this I'm saying. So the kind of problem with this is dimensional. It's only dimension. This is a Boyle's theorem. So I'm trying to give you the kind of what I'm thinking of it. I'm going to do this properly. So the lepton measures is a own plane. Its own dimension. It's not just own dimension. So you think of the lepton. The lepton says obviously these have their own dimensions. What are leptons? So let's start with the definition stuff. So we're gonna have this kind of diagram. This is really an XYZ diagram, but you gonna have definition to it. So I'm gonna keep it straight. So leptons are what? Basically left origins. You get a lattice. So a lattice is like a quantum lattice or a quantum field. Not foam, a quantum field. So quantum field lattice. So get a sparse lattice. A sparse. Let's just make a tomographic lattice. Let me get a lattice. A lattice is what? Divided by what? A what? An eigenlattice. An eigen. This is called an eigenlattice. Eigen. So this measures nothing. Measurement of nothingness. Nothingness. Because when you're measuring pressure, there's a volume associated with that pressure, and that's what you're measuring. That's basically something has to go somewhere. Something has to give. Let's go to something has to give. Pressure or the volume. You get something that a ratio of something that brings on a system. It's like resolving kind of 2 systems in one, but they are working on 2 different kind of axes. For example, if electrons work on the plane on the XYZ, on the x-axis, and basically working on the plane, the geometry of the plane, the lattice field, that is one field of them. So what is what's an anidode? No, wait, an anidode is positive. Anidode. It's basically negative, and it's just negative charge. It's just an electron translation, but it's basically working in gravity, quantum system, basically gravity. But gravity, we don't have graviton. We have something that's a field or a quantum field, which is the kind of equilibrium of the system. So it works basically. It's just everything's just statically charged. It's just the electron, definitely equilibrium structure. But basically you have the stationary kind of concept, which is a graviton. Graviton is just there's no graviton in standard model of physics, and that's why I hate the kind of when people say graviton, because you don't have gravitational particle and you don't have gravity wave. You have a lepton, which is the gravity state of negatively charged electrons. At the equilibrium, nothingness, which of no sense, and that's all standard. So if you say 9.9 G, 9.8 G, that's gravity, you're measuring what? Electrons, and that's what I think of. You don't ever say gravity is as a policy in this framework. That's what I'm saying. I'm gonna give you guys the thing I'm saying now. I think I'll just start a new video. Like this was just annoying me. Which is wrong. Let me start a new video. So you don't say nothing. But let me just say let me start this video.